So let's see the audio. Yes. So welcome back. It's now time for Andreas Gamborg, who is Director of Energy Machines Wings. He's located in Denmark, but sadly could not be together with us today. Hi, Andreas. Welcome. I will unmute you now for your phone. Yeah. No, okay. Should be able to speak.
Okay.
Yeah.
Thank you. Yeah, I'll share my presentation. I can only see my presentation, so let me know if something is missing. So first and foremost, thank you for inviting us. It's been very interesting for me to learn about other companies and what people are working on with smaller wind turbines. And I recognize some of you from LinkedIn. I think I'm connected to a few of you. So my name is Andreas Gamborg. I live in Copenhagen. I work here in Copenhagen. I represent Energy Machines Wind. Energy Machines Wind is a continuation of Vertical Wind AB, which was a Swedish company that built a 200 kilowatt vertical axis wind turbine in Falkenberg. It didn't go so well. They had several issues, especially with the tower. It had a wooden tower that was 45 meters tall, and it had issues with the icon frequencies. That's why you see these guide wires on it. This is an image of that turbine. It's no longer there. So Vertical Wind was acquired in 19. I took over the company in 21. And currently we're 3 employees, and then we have support from Energy Machines. Energy Machines is our mother company. They produce heat pumps and cooling systems for large commercial buildings. So if we need help with electronics or similar, we can go ask Energy Machines. So what do? We design and manufacture vertical axis wind turbines. Our main technology is our generators. And we both make drag-based turbines, small ones, and then we make larger lift-based ones. And we have a focus on making these turbines out of environmental friendly wind materials. So that's what I'm going to talk about a little bit further. And why do we make vertical axis wind turbines? We think there is a market for smaller vertical axis wind turbines, or medium size. We think vertical axis wind turbine will work up to around 100 kilowatt. Anything bigger, you will have some weird load cases, and it will become quite difficult. And you don't get the benefits of the vertical axis wind turbine. They're very simple. They have very little moving parts, and yeah, I have plotted here some reasons why you should have vertical axis wind turbine. As you see here, we do a small one, the drag at the bottom, and then we have our larger lift turbine on the right there. So the drag turbine, we have ended up with this design. We started in making one that was a little bit bigger, but now we're down to 1 meter sweep area. We call it 100 watts. We don't want to overpromise too much. There's a lot of these vertical axis drag base that are being sold that can't really hold the promise of the production numbers. So we are making this turbine out of ABS or plastic, a polymer that's UV resistant. It's vacuum formed and in a modular shape, so you can stack them in different heights if needed. The current one we deliver with a battery pack, and we mainly do it for off-grid installations. Later on, we want to install them on tall buildings, very tall buildings where there's a lot of wind. And we want to install them in clusters. Putting one turbine on one roof doesn't really make a whole much of sense. Yeah, we are currently testing this turbine in Copenhagen, Amagerfællet. There's a new area being built there, very controversial area. But there we have placed one on a rooftop. and as you see in the video here, it actually produces a little bit up there. Then we have two installations in Sweden, one in Halmstad and one in Utter, south of Stockholm, and those are off-grid. And the one on Utter is powering some irrigation system. The one in Halmstad is powering a web camera that we use to look at our bigger turbine. So this is the prototype of our lift turbine. This is a 10 kilowatt version. We're going to scale it up to 25. The economy of a 10 kilowatt is almost the same as a 25, so we have chosen to scale it up to a 25 in the future. It's designed after class 3. It's a stall turbine. We would like to pitch the wings, but we are not going to do it for a while. We think it's very technically difficult. The rotors are made of aluminium, extruded aluminium. We have built our own generator. That's some of the technology we got from vertical wind. So we design and build these generators ourselves. I should mention we also built the generators for the smaller turbines. They are based on some components that you can buy commercially, and then we sort of built them out so we can use it as generators. Later on, we hope to make a 2 kilowatt turbine that is going to use the generator from our drag turbine and the control system for our drag turbine. I should mention the control system for the little turbine is something we also have designed and built ourselves. We are looking for a manufacturer for that one at the moment. Yeah, the lift turbine is made from, the wings are made from aluminium, extruded aluminium profiles, a design that we have made. They're internally reinforced, and they're placed on a tower that's made of glulam, high quality glulam that's pressure treated. And then we mount everything on a steel base that is mounted in the ground with soil screws. And then the question, why do we do vertical axis wind turbines? We think they will require less maintenance, there's less moving parts. There's less need for controls. And the load case is pretty simple until you reach a certain level of size. I know on DTU wind, they call them fatigue machines, but I think that only really accounts for the larger versions with longer blades. The load case we are seeing is centrifugal forces mainly. So that's what we're designing after. So the turbine that was built back in 2011 didn't really succeed. And why can we do it better now? We have better computational software. We do a lot of FEAs. We do a lot of CFD. We have a cloud-based CFDs from SimScale that we use. And then simply there's better production methods nowadays. Things are cheaper to produce, CNC, laser cutters. We use 3D printed parts. Here's an example of one of them. We have winglets on our lift turbine, and we simply just print them out of nylon. Then aluminium quality has improved quite a bit. We use heat treated, of course, and we have done quite a lot of testing on these wings, and they hold up very well. Then we use some very low cost pre-galvanized steel that's often used for solar panel installations called Magnelis. And then for covers, we use UV stabilized ABS. Then the power electronics we use in the lift turbine is standard ABB drives with that are made for motor controls, and they now come with regenerative braking, so that is what we use. Yeah, and as mentioned, some of the tools we're using, we use an engineering model that Uppsala University have made for dimension vertical axis lift turbines. So we've used those for the wings and to estimate the load case on the rotor. Down on the left here, you see some of the results. It's called there's a 2D vortex model and a 3D model. And here's sort of the difference between the calculations. And then we use SimScale for CFD of the smaller turbine and also for the drag load on the towers and in sort of a storm condition. And then we use SimScale for FEA and Creo for FEA. We've done a little bit of simulation of placing drag turbines, the small drag turbines in clusters. There's been a lot of sort of academic papers around this. We wanted to try it out as well. And our hope is to actually test this out in reality soon. Yeah, and that's what it was for me. Any questions?
Thanks, Andreas. Is there any question from the audience? Yes, just a moment that I unmute you. Yeah, you can just unmute yourself now.
Okay. So thank you for the good presentation. I just wanted to wonder about the power coefficient of the turbine, like both of them, the drag one and the lift based one.
Is the efficiency?
Yeah, like the power coefficient or maybe the rated power.
Yeah, so we call it 25 kilowatt 25 because at 11 meters per second, that's what it's producing. It will produce a little bit higher. We've seen that with the 10 kilowatts, and then it's a matter of how much do you want to push the envelope. But CP wise, what we have simulated, and we haven't done full performance testing on the 10 kilowatt, but we are seeing a CP that's certainly above 0.3 and maybe 0.35.
And like I think the important point of a small wind turbine, especially for a vertical axis, that it can start at low wind speed. So I was wondering for your prototype or for your model, at which wind speed can it start working?
Yeah, I don't understand the focus on low wind speed. There's no energy in low wind speed. So so for the we start up the 10 kilowatt at around 4 meters per second. We don't feel there's any need to start it up at 3. The drag turbine just starts whenever it wants. And then it's a matter of getting enough voltage to start up the boost and so on in our power system. So CP for the drag turbine, which sort of the sore topic, because it's low, it's very low. Yesterday there was mentioning of a flower turbine and the other wind.
Yeah, they also have a very low power coefficient as well.
Yeah, they're pretty low. So we have done quite a lot of simulation, quite a lot of optimization. I think we are hitting 0.16. So, and I think like what Savonius made back in the day was 0.1 or something, or 0.12. There's not a lot of optimization to be made there. There's simply not. It's not that efficient. So we say we only want to use these where there's turbulence and you, for instance, you're close to a building or something like that. So I have seen papers where they say that they can reach 0.25, but I really don't believe that. We have measured 100 watts at 10, 11 meters per second with our 100 watts. Actually, earlier today, so part of being part of the Energy Machines group is that we have access to a cloud solution. So we get all our data to a cloud solution that we can access online, which is nice.
Okay. Thank you.
You're welcome.
And then there was a question from Mohammed. What is the rated efficiency of the generators you made? Yeah.
So just generator itself, the 10 kilowatt, we are at 0.96. 25 is going to be around the same. And those for the 10 kilowatt, that is actually what we have seen. It's a little bit difficult to measure, but we sort of, when you calculate through the whole chain, we see that is probably correct. Then for the small generator, it's lower. and it's a low speed generator, right? It's pretty big generator compared to the size of the turbine. So the rotor diameter is like 220 millimeter, and I think we get at higher speed we get almost 90%, but probably 85%. And then there's loss in the electronic system as well. So when we talk about start up at low wind speed, we don't want to start up too low because the controller will actually use more energy than the turbine is producing. So we will use the battery. So we have limited the startup wind speed.
Thanks. Any other questions from the audience?
I don't try and understand how you break a turbine for the high wind. Is it store or you use oversized inverter to break it down?
I didn't really hear that.
Yeah.
I did not quite understand how you break the turbine at a high wind. It's just oversized at the.
So the drag turbine, we don't.
Not the drag, the other one.
Oh, the lift, yeah. So this is the reason why it's not running currently. We had so the generator is mainly the braking. It's doing the operation braking, and then we have an emergency disc brake in the top of the turbine. So it sits all the way at the top, and there is a hydraulic disc brake. And now we have added a parking brake. We saw an issue that if there's no power on the grid, we will only have one brake, and we didn't feel that was safe. So we have added a parking brake that is spring applied, and we are implementing that right now. So that, so yeah, operation, we use the generator. Emergency or no grid, disc brake, that doesn't work. We then use the parking brake. It's when you see the turbine spinning and you're close to it, that the big lift turbine, it is a quite big thing that is moving around. And since it's aluminium, it's not the lightest. So it has a lot of inertia. The generator is also pretty heavy. Yeah. There's of course there's a drive shaft connecting the rotor at the top to the generator at the bottom. So the generator is sort of helping the foundation quite a bit. It can stand by itself up to 25 meters second wind. Yeah. There's when we started out, there was a question we couldn't really find a good answer to. Is a lift vertical axis wind turbine, is that self-starting? And the answer is sometimes. If we see gusts, it will actually start moving by itself. It's not supposed to, but it actually is. So that's something you have to think about with safety.
Just to complete, when you say starts, I mean it starts and then, but it does not reach the rated RPM. Starts but stay low.
No, it goes. So normal the
blade that I hard believe. I mean, you should have a very, very strong wind. I don't know how much.
So it's we produce the most power at 3.5 to 3.7 TSR. If we don't load the generator and it's just free spinning, we hit TSR 7. That's where it want to go. So it goes
by itself, without helping.
By itself, it will. If it starts moving a little bit, it will just pick up in speed. We tried it because we needed to test the brake, and it is not fun. It goes fast. That means it will reach its sort of max allowable speed at 7 meters per second. Right. So it will. We don't want this 10 kilowatt to go more than 90 RPM. Maybe 100, but then if we reach 100, we slam the brakes, and that is due to the low case, the centrifugal forces. The wings will fly off if it rotates too fast as well. Yeah.
Okay.
Hopefully, we will install the 25 outside Copenhagen beginning of next year.
Okay. And we would be happy to, if you have the chance next year to join us in person, that would be amazing. Then we could to discuss, and you can be part of the networking sessions as well. So
Yeah, I see that I should have been here in person, but it's a very busy time.
yeah, we're fully
We're not
understand.
that many people, so I do a lot of the designing myself.
It was also a late notice, so no
Yeah.
problem.
But thank you for the invitation. This has been very interesting.
And thanks for
And
your
I'm gonna
presentation.
reach out to some of you later on.
Sure.
Yeah.
You're welcome. So thanks a lot.